Okay, so we have Kazuya Mameda talking about the novel chiral structure realized by rotation.
Okay, so first of all, I'd like to appreciate the organizer for giving me this good opportunity. And I'm Kazuya Mameda from the University of Tokyo. Today, I'd like to talk about the crucial effect of the rotation in the QCD, especially the crucial effect for the chiral symmetry breaking. This talk is based on the collaborations with these guys and these guys. So unfortunately, I have uploaded this paper in this morning. So you can read this paper tomorrow. Okay, first of all, so we know that many examples the QCD in some environmental effect. So for example, the temperature and density is conceptual the quantity in the QCD thermodynamics. And also we can consider the finite state angle. The QCD with finite state angle is a very hot topic which is related to heavy ion collision experiments. And also we can consider the magnetic field and the gravitational field as external sources. So today in this work I'd like to consider the rotation as a kind of an external environment. And I pick up the magnetic field and the rotation, and we discussed about the QCD thermodynamics in these environments. So the magnetic field is very important for the QCD thermodynamics because we know the actual example where the huge magnetic field exists. For example, in heavy ion collision we can create the huge magnetic field, and also there is a huge magnetic field in magnetar on the surface and inside. The more important thing is that these two systems has a rapid rotation, and which is related to the so about heavy ion collision, we can discuss the chiral vertical effect. So then, if you discuss these two systems, then you have to consider not only the magnetic field but also rotation. So before going to our discussion, let me review the magnetic effect to the chiral symmetry breaking. So suppose that you have attractive interaction between the quarks or fermions, and you have also large magnetic field. Then magnetic field drastically changes the structure of the chiral symmetry breaking. Namely, as the magnetic field increases, then dynamical mass is enhanced by a magnetic field, which is named magnetic catalysis. On the other hand, if you consider the finite density system, then the situation is drastically changing. So in this case, magnetic field plays a role to suppress the dynamical mass. This phenomenon is called magnetic inhibition or magnetic catalysis. So based on the usual discussion of the magnetic inhibition or inverse magnetic catalysis, we expect the magnetic inhibition by rotation. So because if you have rotation, then energy dispersion is shifted by this value. So this is rotational energy. And we can consider this shift as an ineffective chemical potential. So in this sense, in the rotating system, so we have so in rotating system, magnetic inhibition realized. And we named this phenomena, novel phenomena, rotational magnetic inhibition. Then in later parts, we discussed this novel phenomenon. So first, this is the Dirac equation under the presence of the magnetic field and rotation. And now we are consider that there is the magnetic field along to the z direction, and also rotation axis is along to the z direction. The magnetic field is included in the covariant derivative d, and the rotational effect is included in the gamma mu and d mu, and covariant derivative gamma mu. So this comes from the so this corresponds to the covariant derivative in the curved space. And now we take the metric given by this one. And solving this Dirac equation, then we can get the dispersion relation of the fermion. So as we are expected, we have the rotational energy like chemical potential. And also in the right-hand side comes from the random quantization. So based on this setup, we discussed the NJL model under the presence of magnetic field and rotation. So this is a NJL model Lagrangian. And in the mean field approximation, we can get the one-loop gap equation. Then, solving this gap equation, we can obtain the dynamical mass as a function of magnetic field and rotation. And so we know that NJL model infinite density leads to for weak coupling. The NJL infinite density leads to the magnetic catalysis. On the other hand, for strong coupling, NJL infinite density leads to magnetic inhibition. So following this definition, we can check these two cases with rotation. The first is a weak coupling case at zero temperature. So these three arrows means that dynamical mass is increased by the increased as a magnetic field increased. So this is corresponds to the magnetic catalysis. And also, if you have large rotation, then dynamical mass is suppressed. So this is quite similar to the case of finite density. The next is strong coupling result at zero temperature. So oppositely, for finite with finite omega, you can see the suppression of the dynamical mass as the magnetic field increases. So this is a rotational magnetic inhibition we made. And finally, so we have to mention that how rotation affects the fermions. So So similarly to the finite density case with finite chemical potential, the omega is introduced into some dynamics through the Fermi distribution function. Therefore, at the zero temperature, omega appears only in the step function. So it means that if there exists the mode that satisfies this relation, then rotation affects the fermion dynamics. So otherwise, fermion does nothing. Rotation does nothing. And first, let us consider the huge magnetic field compared with the scale of the system size. In this case, the wave function of fermions is quite localized. It means that R is finite, but R can be regarded as an infinitely large quantity. So in this case, we can realize the lambda quantization, and we can get the eigen mode like this. And this dispersion means that this dispersion has a lambda zero mode. So in that sense, the epsilon can be zero. So in this sense, the rotation with some huge magnetic field always affects the system. However, the case without a magnetic field is completely changing, because the wave function is no longer localized. So therefore, the R should be finite. So then, the eigenmode of the fermion is given by this one. Now, psi R is a wave function of the fermions, and JL means the Bessel function, L's Bessel function. And if you impose the Dirichlet type boundary condition, then the perpendicular momentum is quantized by this one. So psi LK means that the case zero of the Bessel function JL. Okay, then now we can check the IR mode, aperiodic mode. So taking the M equals PZ equals 0, then the lowest energy, lowest mode given by the psi L1 over R. And so now we are considering the rotation. Then we have the causality, omega R smaller than 1. So it means that IR mode, the lowest IR mode should be smaller than this value. And surprisingly, this quantity is always positive because of the property of the Bessel zero. For example, psi 01 equals to 2.4 blah blah blah, which is larger than 1/2. So it means that rotation itself leads to nothing. I mean, without the magnetic field, the rotation cannot be changed as some dynamics, at least at zero temperature. And this is summary of my talk. The first, rotation itself never changes the dynamics, at least at zero temperature. However, once magnetic field is applied, then the system with magnetic field and rotation is quite similar to the magnetic field with finite density. And for high magnetic field or at the high temperature, we can ignore the boundary effect. So for high T case, the Virenkin is discussed the vertical current for high T case. And if you want to discuss the thermodynamics with a small electron, small magnetic field, or at low temperature, then we have to consider the boundary effect. Okay, thank you very much.
Okay, questions? Any questions? Yeah.
So we were studying constant magnetic fields in a constant rotation.
Yeah.
I wonder whether there are constraints because magnetic fields and rotations are not totally independent, because magnetic fields transform as a tensor rank 2 under Cauchy transformation. So there should be, just from relativistic invariance, some constraints between the systems, but probably not being constant.
In the rest of range, independent. They are independent, of course. And so after the transformation of the coordinate, of course, these two are related. Yeah, this is included in this calculation.
Okay, thank you.
Okay. Any other questions? That's the question I had. Question. Okay. Thank the speaker again. Now for the before the closing session.
Good. And people should stay? Sorry? No.
No.
Well, we have the poster session now outside, and there will be wine and some crisps, I guess.
Okay, so that's it. Thank all the speakers. This is supposed to be